situation that we have here is a block that is sitting on top of an incline. The incline and the block have a friction between them. The incline has an angle theta with the horizontal, and the coefficient, we're going to describe the stickiness of the block and the surface with the coefficients mu sub s and mu sub k. Remember that mu sub s stands for coefficient of static friction, and mu sub k stands for coefficient of kinetic friction. So what we're going to do here is we're going to imagine that we tilt the angle, increase the angle for the incline until the block starts to slide. Okay, so you're going to notice if you ever do this kind of experiment with any object on an incline that eventually there is an angle at which the object starts to slide down the incline. So if we do this experiment, then the question that we have here is whether we can figure out what is the coefficient of static friction if we measure the angle at which the block starts to slide. I'm going to call that theta maximum. Okay, so that's our job for this problem. So we're going to start with reminding ourselves that we're going to start with an angle that the block doesn't slide at. So for this angle theta, the block is just sitting still on top of the incline. There is no acceleration. And as usual with Newton's second law problems, we're going to draw a free body diagram. We start by drawing the forces acting on the object of interest, in this case the block. So the first one is the interaction with the incline, which gives us a normal force, F sub n. We also have the interaction between the block and planet Earth, which we call gravity, mg. And of course, the interaction with the incline also gives us a tangential component that we call the force of static friction. Again, this is static friction because at this point, the block is not sliding. The angle theta has not reached the maximum value that, at which it starts to slide. So the block is just sitting there, static friction. Next thing that we do to complete our free body diagram is to draw the x and the y axis to choose them. This was discussed before. The best choice for this kind of problem is to tilt the axis with the x pointing down the incline and the y pointing perpendicular to it. One more thing that we're indicating there is the angle theta that mg, the weight of the block, makes with the y-axis, with the perpendicular to the incline. You should convince yourself that those two angles are the same. So with our free body diagram complete, we do the next step, which in every case will always be to write Newton's second law for the x direction and Newton's second law for the y direction. So let's start with the x components. So the sum of the forces in the x direction equals the mass of the block times the acceleration of the block in the x direction. Notice that in this setup that we have right now, where the block is just sitting on top of the incline, not moving at all, the acceleration, therefore, in the x direction should be 0. So what are the forces in the x direction? Well, the weight has a component along the x direction. As you can see in the picture, that's mg sine theta. We also have a force pointing in the x direction, but in the negative x direction. So we're going to write it as minus Fs. That force is the force of static friction. So mg sine theta minus Fs equals 0. Again, 0 because the acceleration in the x direction is 0 because this block is not moving. So this tells us that the force of static friction in a situation like this will be equal to the component of the weight along the incline. And now let's think about this. What happens when you increase the angle theta? So as theta increases, you know that the function sine of theta should increase. Remember that if theta is 0, the sine of theta is 0. But as you increase theta and you make it all the way to 90 degrees, the sine of theta is going to increase all the way to 1. So as theta increases, the sine of theta increases, which makes us think that the force of static friction is going to have to increase. As we increase the angle of the incline, the force of static friction is having to increase to be able to hold the block in place. So this makes us think that because the force of static friction has a maximum value, this is one of the basic equations for friction, that says that the force of static friction can have any value between 0 and its maximum value, which is given by the coefficient of static friction multiplied by the normal force. This is one of the basic equations. So if the block starts to slide at a particular angle, that must be because at that angle we have reached the maximum value that the force of static friction can be. And that maximum value is mu sub s times the normal. But at this point we still have to figure out what is the normal. We can use that equation, mu sub s times Fn, which we don't know yet, but mu sub s times Fn, which is the maximum force of static friction, is going to be equal to mg sine theta. So we can write mu sub s Fn equals mg sine theta maximum. Now notice that I'm not calling that theta any theta. This is a special theta. Only at the theta maximum we are allowed to use this equation, because this equation is only valid when we are at the extreme case, when the force of static friction is having to use all of its strength, which is mu sub s times the normal. So we have this equation. I'm going to call it equation number 1, that relates the coefficient of static friction with the maximum angle. But the step that is missing here to be able to tell what is the coefficient, how is the coefficient of static friction related to the maximum angle, is we have to figure out what is the Fn, the normal force, and replace it in this equation. So that's what we're going to do right now. We're going to go to the sum of the forces in the y direction, Newton's second law in the y direction, which is equal to m times the acceleration in the y. Again, because the block is not moving at all, we know that the y acceleration is 0, and we have forces in the y direction, clearly Fn, and we have the component of the weight perpendicular to the incline, that is mg cosine theta, but we plug it in with a minus sign because it's pointing down. So Fn minus mg cosine theta equals 0, because the block is not moving, it's 0, and we can then therefore figure out that Fn is mg cosine of theta. So that is the value of the normal force, which we can now plug in the equation number 1, replace Fn with mg cosine theta, and the equation that reads on top that mu sub s times mg cosine of theta maximum equals mg times the sine of theta maximum. Okay, so in this equation we can cancel the mass, we can cancel g and divide by cosine of theta max on both sides, and we have that the coefficient of static friction is equal to sine theta max divided by cosine theta max, which you all know there's a short way to write that. That is the tangent of theta max. So so mu sub s equals, let me clean this up a little bit. So mu sub s is going to be equal to the tangent of the theta max, the angle at which the block starts to move. Mu sub s equals tangent of theta max. So notice that this equation is giving us a nice way to measure coefficients of static friction. We just put the object that we're interested in finding its coefficient with the surface of the incline, we put it in an incline, we increase the angle, and the moment when at the angle at which the block starts to slide, the tangent of that angle is going to be the coefficient of static friction. Okay, so that's a nice result. Now we're gonna look at the situation when the block is already sliding. Okay, so if the block is already sliding, we don't have the friction is not going to be static, it's going to be kinetic. So let's take a look at that situation. So suppose that the block is already sliding down the incline. So the block has some velocity, but there's going to be some acceleration also, and we would like to know how is the coefficient of kinetic friction, mu sub k, related to the acceleration of the block. That is our next task in this situation. All right. So as the block goes down, slides down the incline, it will also accelerate. And if we could measure that acceleration, then what would be the value of the kinetic friction coefficient that we can deduce? So let's tackle this again. Again, we always start by looking at the free body diagram. You should be quite familiar with this free body diagram for this situation now. So we have the normal, and we have the force of friction, kinetic in this case, and we have the weight of the block, and we're going to use Newton's second law. So Newton's second law in the x direction says the sum of the forces in the x equals the mass times the acceleration in the x. Do not make the mistake of making or canceling, saying that the right hand side is 0, because there is an acceleration in this situation. Newton's second law says that the right hand side of the sum of the forces in the x direction always equals the mass times the acceleration in the x direction. So make sure you don't cancel that. We're just going to call that acceleration in the x direction just a, because the block doesn't accelerate in the y direction. We know that for sure. The block stays on the incline. So in the x direction, then we have the component of the weight in the x direction, that is mg sine theta. And we have the force of kinetic friction in the negative x direction, so minus Fk. And those are all the forces with an x component, so they should equal the mass times the acceleration. And the equation then says mg sine theta minus the force of kinetic friction is equal to the coefficient of kinetic friction times the normal. So mg sine theta minus mu k times Fn equals mass times acceleration. We're going to call that equation number 1. As before, we would like to figure out what is the force of the normal force, and replace it and figure out what is the acceleration and how is it related to mu sub k. So from the y components, again, Fn minus mg cosine theta is 0, as we did before. So Fn equals mg cosine theta, which we can replace there, and we get the equation mg sine theta minus mu k times the normal, but the normal is mg cosine theta equals ma. Notice that every term in this equation has a mass, so we can divide everywhere by m, canceling it. And we can write that the acceleration, therefore, of that sliding block is g sine theta minus mu k g cosine theta. And we're pretty much done. We could just factor out a g if we wanted to, and we get the equation a equals g sine theta minus mu k times the cosine theta. So you can imagine that in an experimental situation where you set up a block and the block slides down an incline, you can imagine that if you measure the acceleration and then you measure the angle of the incline, knowing that g is 9.8, that would allow you to find what is the coefficient of kinetic friction between the two surfaces. So basically what we have discussed so far is a method, or I guess two methods, to find out the coefficient of static friction and the coefficient of kinetic friction between two surfaces. First method discussed here gave you the static friction coefficient, and the second method here gave you a way to measure the coefficient of kinetic friction. Alright guys, I hope this is going to be useful for you when you're doing the lab. Take care, I'll see you in the next video.